Good morning, ladies and gentlemen. My name is Kudaibergenov, and I represent the Private Research Institute of Polymer Materials and Technology from Kazakhstan. Before starting my presentation, let me please to thank the organizers of this conference, especially two professors, Sergey Filippov and Vitaly Khotariansky, for kind invitation and introduction. My topic is devoted to macroporous amphoteric cryogels, and the application is flow through catalytic reactors. In my topic, I will consider the next topics: types of polyampholites, structure of polyampholites, macroporous polyampholites, immobilization of metal nanoparticles within macroporous amphoteric cryogels, cryogel immobilized metal nanoparticles in hydrogenation of aromatic nitro compounds, and cryogel encapsulated catalase in oxidation of aliphatic alcohols, and the concluding part. Polyampholites belong to unique class of polyelectrolytes containing in macromolecular chain acid base or anionic cationic groups. The first fundamental monograph on polyampholites was published in 2002 in USA by Kluwer Academic Plenum Publishers. Since then, approximately 1,300 records were found on this topic, and according to database of Web of Science, 10 top authors contributed to the subject are listed below. In 2021, the second fundamental monograph devoted to polyampholites was published in Kazakhstan. Polyampholites can be divided into three major classes: annealed, quenched, and beta-ionic. Annealed polyampholites consist of acid-base monomers that are ionized independent of pH, for instance, copolymer of vinylpyridine and acrylic acid. Quenched or strongly charged polyampholites represent amphoteric macromolecules consisting of static positive and negative charge and slightly depend on pH. This is one of the examples of this quenched polyamphfolite. Beta-ionic or tetraionic polyampholites contain identical numbers of acid base of fully charged anionic cationic species in the same monomer units. In its turn, the polymeric beta-ins are divided into poly, carbon, sulfur, and phosphobeta-ins. Here I want to mention Professor Andrei Lashevsky, who have made outstanding contribution to polymeric beta-ins or polytetraions. The macromolecules existing via compensation of the cationic anionic monomer pairs without counterions are also belong to tetraionic polymers. The microstructure of polyampholites can be represented as random, alternating, graft, diblock, triblock, multiblock, dendritic, and stars. Here, this is some examples of such kind of polyampholites. Amphoteric, last year, our attention is paid to amphoteric cryogels that can be obtained by conventional radical copolymerization in cryo conditions. On the microscopic level, moderately frozen molecular solutions can be represented as heterophase systems containing the polycrystals of frozen solvent. For instance, water crystals. And some unfrozen fraction called unfrozen lipid microphase, where the monomers are concentrated. Gelation can only occur inside of unfrozen regions due to extremely high local monomer concentration, while the crystals of frozen solvent play the role of porogens. The pore size of cryogels can vary from several to several hundred microns, for instance, from 10 to 100 microns. Due to porous structure, cryogels can retain up to 74% of water molecules in large pores, and such big pores can be used as flow-through catalytic reactor. Functional groups of amphoteric macromolecules can capture metal ions stabilized by coordination of ionic bonds, and after reduction of metal ions, for instance by sodium boron hydride, we can see the metal clusters stick on the wall of macroporous, and such metal clusters can play the role of catalysts. Another route of metal immobilization is immersing of cryogel sample to aqueous solution of tetrafluoroauric acid and boiling. Due to participation of functional groups of polyampholytes in reduction of metal ions, the colorless cryogel sample turns into red color that is specific for plasmonic resonance effect of gold nanoparticles. The gold nanoparticles are uniformly distributed in both surface and the inner part of macropores. Most of them are triangular, hexagonal, spherical, and rod-like species. The average size of gold nanoparticles is varied from several nanometers to several microns. Here you see this is a pristine cryogel and the same cryogel with immobilized gold nanoparticles. And gold nanoparticles immobilized within the matrix of amphoteric cryogels were used for hydrogenation of nitroaromatic compounds in mild conditions. The mixture of substrate and the reducing agent passes through the cryogel sample containing immobilized gold nanoparticles through the pores. The free flowing of reaction mixture through the cryogel pores under gravity creates enough contacts between the catalyst and the substrate. The efficiency of such catalyst was tested for two model reactions: reduction of para nitrophenol and para nitrobenzoic acid, shown here. The reduction of para-nitrophenol is easily monitored by UV visible spectroscopy because para-nitrophenol absorbs at 400 nanometer and the nitrophenol, aminophenol at 300 nanometer. And this is very convenient to calculate, to follow by reaction kinetics and to calculate the activation energy of reaction. After repeated passing of the mixture of para-nitrophenol and the sodium boron hydride, we reached up to 95% conversion of substrate to final product. However, it should be noted that the mixture of paranitrophenol and the sodium borohydride fluxed through the cryogel samples doesn't produce para-aminophenol in the absence of immobilized gold nanoparticles. Hydrogenation of para-nitrobenzoic acid to para-aminobenzoic acid represents a great interest because para-aminobenzoic acid is precursor for local anesthetic drug novocaine and decaine. Hydrogenation of para-nitrobenzoic acid by gold nanoparticles yields three products. The first one is para-aminobenzoic acid that is produced from the first to fifth cycle hydrogenation. The second one is other compound that is formed from the 6th to 12th cycle. Also, we observe the formation of condensation product of para-nitrobenzoic acid. This is a dipeptide. In case of palladium nanoparticles, we observe the formation of only para-aminobenzoic acid without any byproducts. And the conversion degree of para-nitrobenzoic acid depends on molar ratios of substrate to reducing agent. When the molar ratio of substrate to reducing agent 1 to 50, the average conversion after 10 cycles is approximately 40%, while the conversion is full when we have the big excess of reducing agent. It means that the excess of reducing agent is better for hydrogenation process. The successive hydrogenation of para-nitrobenzoic acid and the successive hydrogenation of para-nitrobenzoic acid at various temperatures allowed us to determine the rate constants and calculate the activation energy. It was found that the activation energy in our case is equal to 38.83 kilojoule per mole. And this value is close to found in literature, 35 plus minus 10 kilojoule per mole, when para-nitrobenzoic acid was reduced by hydrogen over polymeric composites containing palladium nanoparticles. One of the key problems in catalysis is leaching out of metal nanoparticles from the catalytic system. As seen from this slide, in the course of 10 cycle hydrogenation of para-nitrobenzoic acid, the content of gold nanoparticles is reduced due to leaching out of gold nanoparticles from the cryogel matrix. Let us see some images of gold nanoparticles on the surface and longitudinal sections of cryogel spacemen after 10 hydrogenation cycles of substrate are completely different from the initial state. Recently, we were able to encapsulate catalyzer, enzyme catalyzer, within strong charged polyamphoride cryogel derived from anionic and cationic monomers. Catalyzer is well known and the most powerful enzyme for decomposing of hydrogen peroxide to water and oxygen For instance, one molecule of protein can split 5 million molecules of hydrogen peroxide per minute. Using the same principle, as I mentioned, flow through macroporous cryogel reactor, we used cryogel encapsulated catalyzer for oxidation of isopropanol and normal butanol by hydrogen peroxide in mild conditions at room temperature and atmospheric pressure. The chromatographic analysis reveals that the oxidized product of isopropanol is acetone, and the oxidized product of normal butanol is butyraldehyde, and with rather high yields, 90% in case of isopropanol and 80% in case of normal butanol. Based on commonly accepted approach, it is proposed that the following mechanism of isopropanol oxidation, or this is alcohol oxidation, isopropyl oxidation to acetone, and the oxidation of normal butanol to butyraldehyde. At first, the hydrogen peroxide molecule coordinates with trivalent iron, heme iron, and oxidizes to 4-valent iron with P cationic porphyrin radical and molecular of water, this route. Then the porphyrin radical generates the active hydroxyl radicals that attack the hydroxyl groups or hydrogen atoms of alcohols, converting them to either acetone or butyraldehyde. The proposed mechanism is not contradictory to generally accepted mechanism of oxidation of alcohols by free catalyzer. Oxidation of isopropanol by hydrogen peroxide was performed by amphoteric cryogel itself without immobilized catalyzer, and by free catalyzer without cryogel matrix in homogeneous condition. At first, the oxidation, as you can see from this picture, in both cases the conversion is extremely low and doesn't exceed 5 or 6%. It means this is the cryogel samples without catalyzer doesn't work. Also, the free catalyzer, this is the doesn't work without cryogel matrix. It was also interesting to evaluate the influence of pH, temperature, and the volume ratio of substrate to oxidizing agent on the conversion of isopropanol. The optimal pH was found to be close to neutral, 6.4. The activity of cryogel encapsulated catalyzer is high at low temperature, surprisingly. Usually, we know that temperature, this is in favor of formation of temperature accelerates the catalytic conversion. But in our case, we see that the increasing of the temperature sharply decreases the conversion degree. And at low temperature, the conversion degree is extremely high. This is probably connected with exothermic character of oxidation reaction. And the optimal volume ratio of isopropanol to hydrogen peroxide is 1:1 by volume. The excess of either alcohol or hydrogen peroxide decreases the conversion. Also, we checked the reusability or stability of cryogel immobilized catalase in hydrogenation, in oxidation, of isopropanol. And we provided the successive oxidation of several portions of isopropanol. The results show that after the first run, the activity of catalytic system drastically decreases. And the fifth run gives only 1.2% of conversion. In our mind, there are several reasons. The first reason is the activation of catalase by substrate, isopropanol, and product, acetone. The second reason is that in the presence of isopropanol water or acetone water mixtures, cryogel samples collapse and retard the accessibility of active centers with respect to substrate. And the third reason is that catalase is leached out from the cryogel matrix, and in future experiments we will clarify the affecting factors. This slide represents the morphology of cryogel matrix before and after oxidation of isopropanol. And it is seen that after several 5 times oxidation of isopropanol, the morphology of cryogel encapsulated catalase is completely changed. The pores become irregular and bigger, irregular and bigger. The flattened and gross regions are observed. This is probably due to oxidative destruction of amide bonds of cross-linker and side chains of macromolecules by oxygen atoms or hydroxyl radicals that are released as a result of hydrogen peroxide decomposition. Now, let me please to summarize, this is my topic. The flow catalytic reactors fabricated from macroporous gels are a new rapidly developing research area that can be applied for many catalytic reactions, for hydrolysis, hydrogenation, oxidation, etc. The advantage of cryogel samples is minimal volume of catalyst, high surface to volume ratio, energy saving and green chemistry aspects, high productivity, and low cost principles. The porous flow through catalytic reactors can provide cascade type successive synthesis of target products by designing a flow setup consisting of several flow reactors. However, the major drawback of cryogel microreactors is weak mechanical properties. A serious problem represents the chemical destruction of cryogel matrix and the leaching out of metal nanoparticles from the three-dimensional network that can cause contamination of final products with metal nanoparticles. We hope that these disadvantages can be overcome in future researches. Thank you very much for your kind attention.